Okay, so let's do an example and stick some numbers in. Let's imagine we have two of these plates with a positive and negative charge. So let's say we've got a situation like this. Now, this arrangement of charges is what we call a capacitor, and having a capacitor made with these two parallel plates, this is called a parallel plate capacitor. We'll talk more about capacitors later on, and so we'll get a better understanding of what they're doing later on. Let's imagine that we have got a parallel plate capacitor with a potential difference between the two plates of 1 volt. So we'll say the positive plate is 1 volt higher than the negative plate. Let's imagine that we have one electron. So here's an electron, and we are going to push this electron from the positive plate to the negative plate. So obviously the electron is going to be attracted to the positive plate, repelled by the negative plate, so there's going to be a force upward on the electron. We're going to push it downward from the positive to the negative plate. Let's figure out what its change in potential energy is going to be. So change in potential energy is going to be the charge, Q, which is 1 electrostatic unit, so 1e, and it's negative. So that's a charge of minus 1e. Let's actually put that in 3 sig figs. Negative 0.100 E. What's the change in voltage? Well, we're going from a high voltage to a low voltage, so our change in potential is negative 1 volt. So the change in potential energy is going to be negative times the negative is positive, so it's going to be a positive change, 1 E times V. Now that looks like an odd combination. 1 electrostatic unit times a volt. That's actually a very, very useful unit of energy. We'll convert that in just a second. But this is a very useful unit when we're talking about energies for electrons, protons, molecules, things like that. Now, how do we go about converting that? Well, we just need to convert the electrostatic unit into coulombs. Let's remember that 1 electrostatic unit, or again, let's say 1.00. 1.00 electrostatic units is 1.60 times 10 to the minus 19 coulombs. So let's take 1 electron volt, convert the electrostatic units to coulombs, so we'll multiply by 1.60 times 10 to the minus 19 coulombs per 1 electrostatic unit. The E cancels, and we end up with 1.60 times 10 to the minus 19 Coulomb volts, and a Coulomb volt is a joule. So 1 EV, and these are just called EVs for short, rather than electrostatic unit volts. 1 EV is then 1.60 times 10 to the minus 19 joules. And we see this is a very, very small unit of energy. The electron, being a very, very tiny particle, has just a little tiny bit of energy when we move it through a difference of 1 volt. Please keep in mind, though, we'll see these over and over again later on, the conversion then from electrostatic units to joules is the same conversion factor that we use to convert electrostatic units to coulombs. Now let's just think about this. If we were to, so we increase the potential energy, we take the electron, let's imagine we release it, it then accelerates back up here to the positive charge. All of that potential energy is converted into kinetic energy. How fast would this thing be moving once it got back to the positive plate? Well, let's just imagine then that we have an electron with a kinetic energy of 1.60 times 10 to the minus 19 joules, and let's see how fast it's moving when it gets back up to the top. So we set 1/2 mv squared, the kinetic energy, equal to 1.60 times 10 to the minus 19 joules. V is going to be equal to, let's say, multiplied by 2, 1.60 times 10 to the minus 19 joules, divided by the mass of the electron, which happens to be 9.11 times 10 to the minus 31 kilograms. That'll be V squared. V is then going to be the square root of that. Multiply that all out, and what we get is V is equal to 5.93 times 10 to the 5th meters per second. This is about 0.2% the speed of light. Whoops. Okay, now I mentioned that just to emphasize this is very, very fast. So just taking an electron and allowing it to move through 1 volt of potential difference ends up speeding that electron up to a speed of 0.2% the speed of light, about 6 times 10 to the 5th meters per second. That is very, very fast. The bottom line is, as we saw earlier, the relationship between the electrostatic force and the gravitational force is that the electrostatic force typically is much, much larger than the gravitational force. And so when we're looking at the motions of particles under the influence of an electric force, typically we can ignore the effects of gravity because they really are practically insignificant compared to, or sometimes very insignificant compared to the electrostatic forces. Okay, so next question. We know, we derived last time, when we have a point charge, let's say some charge Q, this charge creates an electric field that points away from the charge that has a magnitude of K times Q over R squared, where R is the distance from the charge to the point at which we are determining the electric field. Well, here we have an electric field from this charge. Is there any way that we can determine the potential due to this electric field? Well, when we had the potential within a parallel plate capacitor, the electric field was uniform, and it was relatively easy to determine what the potential was when we have a uniform electric field. This electric field is not uniform. It varies as 1 over R squared. It's very strong close to the charge, gets weaker as we get further away. So, is there any way we could figure out a potential for a point charge with a non-uniform electric field? Well, the fact is that we can, although it takes a little calculus to do it. We won't do that, but we'll just, I'll just give you the answer, tell you what it looks like. Except we need to think about one particular important point. When determining, say, for the gravitational potential energy, we know the gravitational potential energy is mgh. Where is this potential equal to 0? Where is the 0 level of potential energy? Well, that corresponds to where the height is 0. In other words, where do we want to put our ground level, you might say? If we want to do an experiment in here in the lab, we might say the floor is our 0 level. If we're outside, we might say the ground is 0 level. If we're up in the top of a building, we might say we'll set the top of the building as our 0 level. It's completely arbitrary. We have the ability to choose any point we want to be our 0 point. Very much like we can choose our coordinate system to have our 0 origin to be wherever we want. It's arbitrary. Well, where do we want our potential to be 0? If we think about this, if we take a charge, say a positive charge, it's going to be repelled by, say, a positive test charge. It's going to be repelled by this charge here. It's going to be pushed that way. So as we would have to push it in this way to approach our charge here, which means essentially that points in close will have a high potential, points further away will have a lower potential. Where do we want to set our 0 potential? Where do we want to set the point V equals 0? Well, excuse me, typically the easiest thing to do is to set V equal to 0 way out at infinity. So infinitely far away, that's where we'll set our zero potential. Can we do that? Yeah, it's arbitrary. We could set any point we want. We could pick that point to be zero potential. We could pick that point to be zero potential. The one point that we can't pick to be zero potential actually is right on the charge, because that's actually where the potential goes to infinity. So we can't choose that to be zero, but we could pick any other point other than right on top of the charge to be zero. If we do that, if we set it to be zero at infinity, it turns out the potential has a very, very simple form. It's just kq over r. Not r squared, like the electric field, but just kq over r. And this, as a potential, is a scalar quantity. It's not a vector quantity, so there's no direction. Remember, this is just the magnitude of the electric field. To really show the complete electric field, we would have to put the unit vector r hat in there, because electric field is a vector field. While potential is a scalar, it doesn't have any direction. So, there we go. That is the potential for a point charge, and what we'll do next is stick some numbers in here and figure out some values for the potential. Let's imagine that we have a charge at the point 1 meter, 3 meters. So here's a charge. We'll say this is 3 microcoulombs. Let's figure out what the potential is at the point 7 meters, 0 meters. So 1, 2, 3, 4, 5, 6, 7. So let's figure out what the potential is at the point 7 meters, 0 meters. So 7 meters, 0 meters. So right on the x-axis. And this one is 1 meter, 3 meters. Okay. So we know that the potential at this point, due to this charge, has the form kq over r. So we need to figure out what r is. R is the distance from the charge to the point where we're calculating the potential. So it's going to be this distance here. Well, we could figure out that from Pythagoras. We know r squared is equal to 3 meters squared plus, now how many is this? We're going from x equals 1 to x equals 7, so this is 6 meters. 1, 2, 3, 4, 5, 6. 6 meters squared, so that's r squared, so r is the square root of that. Multiply that out, and we find r is 6.71 meters. So, v is equal to what? V is going to be k, 8.99, times 10 to the 9th, Newton meter squared per Coulomb squared, times q, we need to put in the charge in terms of coulombs, so 3 times 10 to the minus 6 coulombs, that's a microcoulomb, divided by r, which is 6.71 meters. Multiply that out, and what do we get? We get v is equal to 4.02 times 10 to the 3 volts. So a bit over 4,000 volts. So that seems like quite a bit. Well, that kind of tells us that typically when things build up charges, they're going to build up very, very small charges. If you, rub your, walk across a rug or something like that, the charges are either going to be very, very small so that the voltages aren't too big, or large charges are going to create very, very large voltages. Okay, so given that charge, that is the potential at that point, something over 4,000 volts, 4.02 times 10 to the 3 volts. Let's try another one. Let's imagine we've got another charge. Let's say at the point 3 meters minus 2 meters. So we're going to come over here, 3 and then minus 2. So this is the point 3 meters minus 2 meters. And let's imagine we've got a charge there of minus 4 microcoulombs. Minus 4 microcoulombs. let's figure out what the potential is at this point due to that charge. So we're going to have a kq over r now, but with a different r. R in this case will be that distance. We can figure out r, again, using Pythagoras. So r squared is going to be 4 meters squared plus 2 meters squared. R is the square root of that, which gives us a value of 4.47 meters. So what's the potential? Do this down here. V is K, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times Q, 3 times 10 to the minus 6 coulombs divided by R, 4.47 meters. Divide that out, and what do we get? Oh, sorry. I'm sorry, I put the wrong charge. I put in this charge. What we need is this charge, right, which is negative 4 times 10 to the minus 6 coulombs. Now, what's our potential? When we multiply this out, notice we're going to get a negative sign. Negative charges give us negative potentials. So, multiplying this out, what do we get? Negative 8.04 times 10 to the 3 volts. So in this case, we had a positive charge. Positive charge gave us a positive potential. Here we have a negative charge. Negative charge gives us a negative potential. Now, what if we had both of these charges? We had a positive charge here and a negative charge here. What would be the total potential due to both of them? Well, we've got the potential due to each. The potential due to both is just the sum of the potentials. So the total potential is going to be 4.02 times 10 to the 3rd volts minus 8.04 times 10 to the 3rd volts, which gives us a total of negative 4.02 times 10 to the 3rd volts. What about the direction? What's the direction of the potential? There is none. Potential is a scalar. We don't have to worry about the direction. So this makes potentials in general a whole lot easier to deal with than the electric field. Remember when we combined electric fields, you'd have to break them down into components, combine the components, and then figure out the magnitude and direction from that. With potentials, because they're scalars, all you have to do is add them together. There's no direction involved. So there we go. We're all done with that. The total potential due to both charges is negative 4.02 times 10 to the 3 volts. Okay, let's take a look at another problem, but let's stop part 2 there.